I'm going to go over in this presentation the rationale for testing, some of the types of tests that we have available to us, and the tools that we use to do testing. The Chrome team has around 200 developers, and we average about 100 commits a day. So with all that code flowing in and out, we need to make sure that stability remains a high priority, and one way to assure that stability is to test the code that we're running. So one of the things that tests do is make sure that the feature that you're running runs the way you expect, and you can't have people hand testing your feature every day. So the tests make sure you don't have any regressions that pop up. Another thing that tests do is they document what your code is expected to do, so that when other people come and read your code, they understand the rationale behind what you wrote and the logic behind it. Tests also guide the design of the code in the sense that when you write tests first, you start thinking about how am I going to implement in this way so that these tests pass. It could modify your design heavily. A big piece of the infrastructure that we have in Chrome are our TryBots. So TryBots are a pool of machines that you can send try jobs to that will take your change list and run them through our suite of tests. They'll mainly run them on the three main platforms, Windows, Linux, and Mac, but it is possible to send in a bot parameter to specify another bot you want to run in. Some of the bots that we have available are Valgrind, Chrome OS, Linux views. So when you're changing code that affects those platforms, it's good to run those tests as well. The main test suite takes about an hour to run on average for the three platforms. So can you mute yourself on that side? So if you want to cut down the running time of your TryBot, you can pass in the T parameter, which takes an argument of the test program name, the filter that you want to use. So for example, if I want to run a specific unit test, I'll pass in -t unit test, and then the name of the test that I want to run. And that means it will only run that specific test, which greatly cuts down on the testing time. There's also a concept for TryBots known as last known good revision. The last known good revision is set by the official builders on the waterfall, and it's the last green build that we had. So whenever we get a green build on all the platforms, the last known good revision, or LKGR, is updated. However, the last known good revision could be behind several revisions from what you want to test, so you can pass in the revision using the -r parameter. Whenever you upload a CL, the try jobs used to be automatically started, but that's no longer the case because we have so many CLs uploaded these days. So you need to make sure that before you commit, you at least run your try job for your latest patch set. That makes sure that any failures that could happen in your CL are cut short, so you'll realize the failures are there before you actually make the commit. That keeps our main tree a lot greener. The link at the bottom of this page is the try server waterfall. So if you don't find your try job on the CL page itself, you can head over to that link, and then you can find your LDAP or your username, and you can see the status of your try job. There are three main types of tests, and I'm going to start with unit tests. These are our lowest level tests. They test units of the code, so a method on an object, such as watchdog.arm at start time. So the unit test for that method would test all the logic paths in that method. Good thing about unit tests is they document exactly what's going to happen in this method for all the input parameters that you could specify, and you verify the output is correct. Unit tests are small, so usually they run pretty quickly, and they also don't run with other tests, so they're isolated, and you only test exactly what you want, and you see those results for that bit of code. As an example, I'm going to use the autofill feature, which has an info bar for credit cards. And now if I were writing a unit test for this, I would be testing the autofill CC info bar delegate class itself, which is the lowest level implementation of this info bar. So there's 3 buttons in this class, and there's a link and there's an icon. So the methods on the autofill cc info bar delegate specify how this info bar is supposed to look. So I could run those methods and make sure that I get the 3 buttons back, the text of those buttons, and make sure the link has the appropriate URL. There's unit tests as a target itself, but there are also unit tests for our other major modules in Chrome, some of which are listed here. There are actually quite a few unit tests, which is important. We need a lot of tests. The next step up in our testing types is browser tests. Browser tests create a browser object in the test so that you can test how your code is interacting with the browser object itself. It's actually a specialized unit test, but there's infrastructure set up so that it loads the browser automatically and you have access to browser internals. They're run in a different process, and the sandbox is disabled. There's a running message loop, so you got to take that in consideration when you run things on different threads. And the default thread is the UI thread. Another thing to take into consideration when you're testing your test, running the test yourself, is that the browser window is not visible by default, though you can specify that it be visible. Going back to the autofill info bar, an example of a browser test for the autofill info bar would be load up an info bar, make sure that the info bar is in the tab that you specified the info bar is in, make sure that there's only one info bar per tab, make sure that you can load up multiple info bars, one per tab, but that there's more than one. You can call the method on the info bar class to close to press the close button, and then make sure that in the browser object, the info bar is no longer there. UI tests are high-level, end-to-end testing, integration tests. They're an example of black box testing in that you don't have access to object internals, and you have to implement the test through an automation proxy. There's an automation API which allows you to control the browser. Now, there are several different ways we use the automation API. The main way is UI tests, which are tests written with the automation API. There are also automated UI tests, which use fuzzing. There's a list of commands that are implemented by the automation API. For example, click a button in the interface, load up a page, load up a new tab, and the fuzzing creates a list of these different combinations and runs them and mutates the list. So you're basically getting all these different actions that you can take with the browser and running those actions and seeing how they interact. There's another test type called interactive UI tests, which are necessary for the Windows bots in that these tests interact with the UI by clicking or moving the browser around, and the bots themselves have to be specially configured to take advantage of this. The last one is PyAuto, which is written by, it's a Python interface for writing automation tests. It's a really easy way to write UI tests in Python. So we'd have an API that loads a web page with the form that we've written. The next API could fill out that form with data that we specify. You would have an API that clicks the button using the actual OS infrastructure for programming the click to happen on a button. And then at that point, you check that the info bar shows up as you expect. The next API could also use the clicking API to simulate a clicking on the save button or the don't save button. For the save button, you want to make sure that the data is saved. There'd be another API to say, is there profile data? Does it match what we expected? And if you click on the don't save button, you also want to check that the CC data, credit card data, was not saved. So whenever you're running your tests and it's not working out exactly as you planned, maybe you get a crash or it's just not functioning correctly, you should be able to debug the tests. On Mac and Windows, it's pretty easy to debug tests using the visual interface, whether it's Xcode or Visual Studio. You just compile the test target and then debug that test target. In Linux, it's possible to do that, but most cases you're going to use GDB. So you pass in the GDB and then the test target itself, and then pass in the GTest filter of the test you want to run with args. then you should be able to step through the test and figure out why the test isn't working like you think it should. We have a few frameworks for writing tests that make test writing a lot easier. GTest is the biggest piece of how we write tests. And it has a lot of functionality for you. You can check out the link at the bottom, and there's a lot of good documentation on that. I'll give an example. So the high-level way you look at tests in GTest is that you have a test program, which would be unit test binary, browser test binary, UI test binary. That's your test program. Your test case would be autofill info bar test, which has many tests inside of it. Each test testing a specific piece of that functionality, whether it be a method on the object, interaction with the browser, or a high-level end-to-end UI test. As an example of the GTest framework, it's really easy to set up a test. You have the test macro, the test case name, and then the test name itself. In this one, we're using assert equal, which is a macro used to check that something is how you expect. It's an assertion, so if the thing that you're testing is not valid, the test itself will stop. We also have expect equal, which will not cause the test to stop if the thing that you're checking is not true. Something that you can use to reduce duplication of code are test fixtures. They're a data setup for every test that you run in a test case. I'll show you an example of that. So QTest is the name of the test fixture. We inherit from testing test. There's two methods that you could possibly override. Setup, you usually want to override. And setup is run at the beginning of each test case. In this setup, we are enqueuing some values into queues, several queues. For this test case, we don't need anything to be torn down. But for example, if you weren't using scope pointers and you had allocated data, in teardown is where you'd want to destroy that data. So using the same QTest test fixture, we have two tests here. Is empty initially, we just expect that the queues are empty, and they are. DQ works, we load up data in our test fixture. So if we go back here, we have the enqueues of each of the queues. And then you expect that you DQ the value you get back. There are a lot of assertions that you can use. This map gives you quite a few of them. The asserts, and then the fatal versions are the asserts, as in they will stop the test and the test won't run anymore. You usually want to do these on things that will cause the test to crash in another way that you don't expect. For example, asserting that a vector is a certain size. You want to make sure, because then you're going to access all the elements of the vector, so you don't want to access those without asserting first. The expect assertions won't cause the test to crash. They'll just cause a test failure if they don't evaluate to true. Another piece of framework that we use is Google Mock. Mock objects allow you to provide an object that you don't want to implement fully. You just want to specify the interaction with that object. For example, in this one, we'll start a personal data loaded observer mock. So this is an observer in a messaging sense. And what we have here is we're going to mock out a method on personal data loaded, which will be called by some method or by some class. And the action that we expect to take is quit UI message loop. We have some assertions inside the action and whatever action we need to take. So we're going to quit the current message loop in this action. In the test, we create a profile and we set the profile info. So inside set profile info, the personal data observer is going to be called, and we expect that call to happen. We didn't have to create a whole personal data observer, though. It's just a mocked object with a mock method. We don't care anything else about the object itself, just that this one method gets called. So we have expect call on the observer object that we care to be called. And then we say will once quit UI message loop. Will once means we expect it to happen exactly once. And we expect the action to be taken as the quit UI message loop. There are will repeatedly, which means after the call to set profile info, the method that you're expecting, the action that you're expecting to happen could happen several times. And that's a good way to specify that. At the end of this piece of code, we need to run the current message loops because we've queued up this call in the message loop, and then we need to get back to that message to be called. So we run the message loop. We have several tools for testing. One of the most useful ones is valgrind, which is a memory error checker. And so memcheck is a tool that checks for things like leaks, uninitialized memory, things of that nature. Using the wrong delete, if you use delete instead of delete array when it should be delete array, that'll notify you of that. And then you can see the command to run it right there. There's also thread sanitizer. Thread sanitizer detects data races, and the command to run that is down there as well. Mostly, though, you don't have to run these yourself in that we have valgrind bots on the main waterfall which continuously run these tests. They take about an hour and a half to run. And they will catch these errors for us. And then once we do, we file a bug and we notify the owner of the code that they have a memory error. So then you can run, once you are notified that you have a memory error, you can run the test yourself to debug it. An important part of testing is code coverage, something we need to keep in mind. Code coverage is how many lines of code are actually executed by your tests. So obviously, the higher your code coverage, the more likely it is you're going to catch errors. Although you can never get, you can get to 100% code coverage theoretically, but even if you do, on average, you only find about half of the bugs because the number of input and output is just too much to test. So there are three pieces of information with code coverage. The number of lines instrumented, which are the number of lines that are actually compiled into your test, including testing code and source code. The number of lines that are covered, which are lines that were hit when you ran your test. The missing piece of information is code that was a part of the source code but is not actually compiled in. And this is something you want to take into account for the different bots. For example, on Linux, if there was a Windows-only test that we don't specify as Windows-only and it's not being compiled on Linux, the instrumentation will think that these are missing lines because they are, and that will lower your coverage. We actually want to have the most accurate coverage that we can possibly have, so there's a way to go in and say, this is a Windows-only test, we don't need to run it on Linux or Mac, so don't count it against us. Incremental coverage is a way of testing for each commit in the tree, how many lines of code are tested in that commit for the additional lines. So any plus line in a diff, how many of those lines are covered? Ideally, we want to have 50% incremental coverage. So in any commit you have of all the new lines, you want 50% of those lines to be tested. At that point, you're at break even. You're not going to be losing coverage, but you're not gaining any more coverage. At some point, we'd want to bump that up to 75%, but 50% is a tough enough target as it is. We're currently working on adding the ability to track incremental coverage and setting that 50% target so that it will be a bot on the main waterfall that will alert any build that has a commit in it that is not 50% incremental coverage. The bot will go red, and the owner of that test will be, or the owner of that commit will be notified that they didn't have 50% incremental coverage. And we're working on that. We're getting pretty close to that. We do have a TryBot for coverage up. There's a Linux bot available right now. And once we get more machine infrastructure, we're going to get a Mac and Windows bot as well. The jobs take about an hour and a half, but it's a good way to see, a good way to find out how much your test affects your code. How good is your coverage for the test that you just wrote? There are 3 bots up right now that run coverage continuously, even if they don't have incremental coverage. They're on the experimental waterfall, which is the link at the bottom of the page. If you go to that page and you search for coverage on the page, you'll see the Mac, Linux, and Windows coverage. Those will give you our current coverage analysis, and you can look at any code that you currently work on to see how good your coverage is. One thing that crops up quite frequently with a project of this size are failing tests. And failing can mean a lot of things. Failing could be an expectation or an assertion doesn't pass in the test. It could be a crashing test, a hanging test. All of these are bad things, but some are worse than others. The fact that we're disabling tests is not a good thing because disabled tests doesn't run at all, and so it's effectively dead code at that point. There are two types of tests that need to be disabled, and those are crashing or hanging tests. And we disable those because the rest of the testing infrastructure does not continue to run. So for example, with unit test, if you crash on the very first test that you run in the unit test, you're not going to run any of the rest of your tests, which is the worst. So for those, it's okay to disable. To be even more specific, you should use platform-specific defines that say only disabled on Windows because it's only crashing on Windows. And you want to be as specific as possible when disabling, so we could still have continued coverage on Linux and Mac. Whenever you do disable a test, or whenever you change the moniker of a test to be disabled, fails, or flaky, you want to make sure that you add a comment to the code, file a bug, and then add that bug to the comments so that whoever comes to look at the test to possibly fix it, they have that bug for reference, which should probably include the log to the failing test. There's a flaky moniker which we should use for flaky tests. Flaky tests fail spuriously, so they might run green for a couple times and then fail, and then go green for a couple more times. They just fail on and off. There's also fails, which is used for tests that fail continuously. The infrastructure behind flaky and fails is actually exactly the same. The benefit to the developers are that you know right when you look at the code, okay, this test is always failing, there's some error that's continuously happening, or there's some sort of flake in the system, it's unknown, but we're going to have to look for a flaky issue here. There's a way to disable or to change the monikers for several tests at one time. So say you have a test that, or several test cases that are only failing or crashing on Mac OS. You can use the skip Mac OS macro, which will take a test name and then to say disabled underscore test. And you use those 2 pound marks to actually put the name of the test in there. And then for every test that's failing for that platform, you say skip Mac OS and then the name of the test. One thing you don't want to do is if there is a Valgrind or a thread sanitizer error, you want to make sure that you don't necessarily disable it at the code level if at all possible. For example, if you have a leak and the Valgrind bot is red because of your leak, you shouldn't disable your test. You should either add a suppression, which is most likely for a leak, or if the test is crashing when only run under Valgrind, you should go into the Valgrind files, which they have a list of tests that should not be run just for Valgrind and thread sanitizer, and you should add your test to that list. So, in summation, we need to write a lot of tests. We need to then write some more tests. We have a lot of tools that you can use. Make the most of them, especially Valgrind, thread sanitizer. If you have a failing test that is failing under one of these tools, use that tool locally to debug it. We need to take care of coverage to make sure that our features are as covered as possible for the things that they need to be covered for. And whenever a test is failing, really think about whether you should be disabling it or marking it as fails or flaky so that we keep our coverage numbers up. So that's about it. Do we have any questions? Okay, thank you very much.